What if everything we can ever see is only a tiny, glowing bubble, 93 billion light years across, floating in an ocean of unreachable space where inflation and dark energy hide entire realities from our sight? Did you know that right now, this very second, there are galaxies shining with trillions of stars whose light will never, ever reach Earth? Not because they don't exist, but because the universe itself is expanding so fast that their photons are fighting a losing battle against the stretching of space. And did you know the observable universe, that sphere we can actually detect, measures about 93 billion light years across, even though the Big Bang happened only 13.8 billion years ago? If those numbers sound like they break the rules, congratulations. You've just stumbled onto one of the most mind-bending, paradigm-shattering truths in all of cosmology. Before we dive deeper, smash that like button, hit subscribe, turn on notifications, and drop a comment right now telling me what you think exists beyond the edge of everything we can see. Because what you're about to discover will rewrite your understanding of reality itself. And I want to know if it changes how you see the universe forever. Look up on a perfectly dark night, far from city lights. The stars seem endless, an infinite sea of light scattered across the dome of the sky. For thousands of years, humans looked at that expanse and believed it truly was infinite, or at least that the visible stars were all there was. Then telescopes came along. Galileo turned glass lenses to the heavens and saw moons orbiting Jupiter, craters on our moon, and realized the cosmos was far larger and stranger than anyone imagined. In the centuries that followed, more powerful instruments revealed nebulae, and then galaxies, entire island universes, each containing hundreds of billions of stars. Edwin Hubble, in the 1920s, proved that these galaxies were racing away from us, that the universe itself was expanding. That discovery shattered the ancient vision of a static, unchanging cosmos and replaced it with something dynamic, violent, and evolving. Fast forward to today. The Hubble Space Telescope and the James Webb Space Telescope have pushed our vision to astonishing limits. JWST is currently capturing light from galaxies that formed when the universe was barely 300 million years old, infants in cosmic time, when the first stars ignited and began forging heavy elements in their nuclear furnaces. These images are not just pretty pictures. They are time machines. Every photon that hits the detector traveled for billions of years across expanding space to reach us, carrying information encoded at the moment it was emitted. When we look at a galaxy 12 billion light years away, we are seeing it as it was 12 billion years ago. The light itself is a historical record, a cosmic archive written in wavelengths. But here's where the foundation cracks open and reveals something extraordinary beneath. Despite these incredible telescopic feats, despite seeing galaxies from the universe's infancy, we are not seeing everything. We are not even close. We are seeing only the portion of the universe whose light has had enough time to travel to us since the Big Bang. That portion, called the observable universe, is a sphere centered on Earth, with a radius of about 46 billion light years in every direction. And double that radius, and you get a diameter near 93 billion light years. That volume contains an estimated 2 trillion galaxies, each with billions or trillions of stars, planets, black holes, nebulae, and all the cosmic architecture sculpted by gravity over eons. Yet that observable bubble is not the universe. It is a horizon, a boundary defined not by space ending, but by time and light speed conspiring to hide what lies beyond. Now you might be thinking, wait, if the universe is 13.8 billion years old and light travels at a finite speed, shouldn't the farthest thing we can see be only 13.8 billion light years away? That would make sense in a static universe. But our universe is anything but static. Space itself has been expanding since the Big Bang, not like objects flying apart through a pre-existing void, but like the very fabric of distance stretching. Imagine dots painted on the surface of a balloon. As you inflate the balloon, the dots move apart, not because they're racing across the rubber, but because the rubber itself is expanding between them. In our universe, galaxies are the dots, and space-time is the rubber. This expansion has profound consequences. When a photon left a distant galaxy 13 billion years ago, that galaxy was much closer to us than it is today. While the photon journeyed toward us, space continued expanding. The galaxy itself was carried away by that expansion. By the time the photon finally arrives at our telescopes, the source galaxy has been swept to a comoving distance of perhaps 30 or 40 billion light years or more. That's why the observable universe has a radius of 46 billion light years, even though the universe is only 13.8 billion years old. The math is not broken, it's accounting for expansion. And expansion is not just continuing, it's accelerating. In 1998, two independent teams of astronomers studying distant Type 1a supernovae, stellar explosions that serve as cosmic distance markers, made a discovery that stunned the physics community. They found that the expansion of the universe was not slowing down, as most had expected due to gravity's pull. Instead, it was speeding up. Distant galaxies were receding faster and faster over time. This acceleration implies the presence of something pervading all of space, something with a repulsive gravitational effect. Scientists named it dark energy, and it now appears to make up about 68% of the total energy content of the universe. Dark matter, the invisible gravitational glue holding galaxies together, accounts for about 27%. Ordinary matter, stars, planets, gas, dust, everything made of atoms, makes up less than 5%. We are the cosmic minority. Dark energy's effect is subtle over short distances, but dominant on cosmic scales. Over billions of years, it drives space apart at an accelerating rate. And here's where the geometry becomes unsettling. Because expansion accelerates, there exists a cosmic event horizon, a boundary beyond which events happening now can never causally influence us. Regions beyond this horizon are receding faster than light can bridge the gap. Not because galaxies themselves are moving through space faster than light. Special relativity forbids that. But because the space between us and them expands faster than light can cross it. And the effect is the same. Their light will never reach us, no matter how long we wait. Think carefully about that. Right now, there are galaxies whose current light is already beyond our future reach. If those galaxies harbor planets, civilizations, entire histories unfolding across billions of years, we will never see them. We will never receive a signal from them. They are forever disconnected from us by the structure of space-time itself. And this disconnection is permanent. Even if humanity survives for trillions of years. Even if we build detectors the size of solar systems or entire galaxies. Even if we develop technology orders of magnitude beyond anything we can currently conceive. Those regions are lost to us, sealed behind an impenetrable barrier not made of matter or energy, but of geometry and time. Let that sink in. The universe is vast enough that entire regions exist in a state of permanent isolation, not hypothetical, not speculative, calculated directly from general relativity and observed expansion rates. But the story gets even stranger when we rewind to the beginning. In the earliest fractions of a second after the Big Bang, cosmologists believe the universe underwent a period of exponential expansion called cosmic inflation. During this inflationary epoch, lasting perhaps 10 to the power of minus 36 to 10 to the power of minus 32 seconds, the universe expanded by a factor of at least 10 to the power of 26, possibly far more. Regions that were once smaller than a proton ballooned to sizes larger than the observable universe today. It happened faster than you can blink, faster than a thought, faster than light could cross the pre-inflated space. Inflation was not proposed on a whim. It was invented to solve specific cosmological puzzles that plagued the Big Bang model. One puzzle is the horizon problem. Why does the cosmic microwave background, the relic radiation from 380,000 years after the Big Bang, look almost exactly the same temperature in all directions, even in regions of the sky that, without inflation, would never have been in causal contact? How did they know to have the same temperature? Inflation solves this by proposing that all the regions we see today were once in close contact, equilibrated to the same conditions, then inflated apart so rapidly that they now appear distant. Another puzzle is the flatness problem. Why is the geometry of space so remarkably flat, with curvature measurements consistent with 0 to extraordinary precision? Inflation flattens space the way inflating a balloon smooths out wrinkles. A third puzzle is the monopole problem. Certain high-energy physics theories predict exotic particles like magnetic monopoles should have been abundantly created in the early universe, yet we observe none. Inflation dilutes these relics to undetectable densities. So, inflation elegantly solves multiple problems with a single mechanism, and the evidence supporting it is strong. The patterns in the cosmic microwave background, tiny temperature fluctuations imprinted by quantum fluctuations during inflation, match predictions beautifully. Missions like COBE, WMAP, and Planck have mapped these fluctuations with exquisite precision, and the statistical signatures align with inflationary models. But here's the implication that rewrites everything about the beyond. If inflation occurred, it almost certainly did not stop everywhere at once. In many inflationary models, once inflation starts, it becomes eternal in some regions. Patches of space stop inflating and become normal, expanding universes like ours, pocket universes, or bubble universes. Meanwhile, other regions continue inflating, spawning new pockets. The process never globally ends. This scenario, called eternal inflation, suggests that our observable universe is just one bubble in an incomprehensibly vast, possibly infinite, inflating multiverse. Now, let me be clear, this is theoretical. We cannot directly observe other bubbles. We may never be able to. But eternal inflation is not wild speculation. It arises naturally from taking well-tested inflationary physics and extrapolating it. It's a logical consequence of equations that explain observed features of our universe. Some theorists even search for potential signatures of bubble collisions in the cosmic microwave background, circular patterns or temperature anomalies that might hint at another bubble brushing ours in the distant past. So far, results are inconclusive. The data constrain how close a collision could have been, but do not rule out the multiverse. Even if we set aside eternal inflation and the multiverse, controversial ideas still being debated, there remains a more conservative, yet still staggering conclusion. The universe beyond our observable horizon is almost certainly much larger than what we see. How much larger? Then we don't know. Observations of the cosmic microwave background by the Planck satellite have measured the curvature of space to incredible precision. The results indicate the universe is spatially flat, or very nearly so, consistent with zero curvature to within measurement error. A perfectly flat universe can extend infinitely in all directions. Alternatively, if there is slight positive curvature, like the surface of a sphere, the universe could be finite but enormous, with its total size far exceeding the observable portion. If the curvature is negative, like a saddle, it could also be infinite. Current data does not allow us to distinguish definitively between these options, but it does tell us this: if the universe is finite, it is at least hundreds of times larger than the observable portion, possibly vastly more. And if it is infinite, then the observable universe is an infinitesimal speck within an endless expanse. Let that settle into your bones. Our entire cosmic horizon, containing 2 trillion galaxies, each with hundreds of billions of stars, might represent less than a trillionth, or even an infinitely small fraction, of the total universe. So what lies beyond the observable universe? The simplest, most scientifically grounded answer is more universe, more cosmic web, more galaxy clusters, filaments, and voids arranged according to the same laws of physics. The cosmological principle, a foundational assumption in cosmology supported by all large-scale observations, states that on sufficiently large scales, the universe is homogeneous and isotropic. There is no special center, no preferred location. The universe looks roughly the same everywhere. This principle is not an article of faith. It is tested constantly. The cosmic microwave background is smooth to 1 part in 100,000 across the entire sky. Galaxy surveys show large-scale structure, walls, filaments, voids, distributed uniformly when averaged over hundreds of millions of light years. There is no evidence that our region is unique or that the universe fundamentally changes beyond our horizon, which means, beyond the observable edge, there are likely more galaxies forming, evolving, colliding, more stars igniting and dying, more black holes devouring matter, more planets, some perhaps harboring life. The cosmic story continues, indifferent to whether we witness it. But let's make this emotionally tangible. Picture the Milky Way, a barred spiral galaxy containing between 100 and 400 billion stars. Our Sun is one ordinary star among that multitude, located about 2/3 of the way out from the galactic center in a quiet spiral arm. On a tiny rocky planet orbiting that star, life emerged, evolved, and eventually produced beings capable of looking outward and asking, "What is all this?" Now zoom out. The Milky Way is part of the Local Group, a collection of about 80 galaxies dominated by us and Andromeda. Zoom out further. The Local Group is part of the Virgo supercluster, containing tens of thousands of galaxies. Zoom out more. The Virgo supercluster is part of an even larger structure called Laniakea, a gravitationally bound region spanning 520 million light-years and containing roughly 100,000 large galaxies. And Laniakea itself is just one thread in the cosmic web. the largest known structure in the universe, a vast network of galaxy filaments separated by enormous voids stretching across billions of light years. All of that, the Milky Way, Local Group, Virgo, Laniakea, the entire cosmic web we have mapped, exists within the observable universe. And the observable universe might be a grain of sand on an infinite beach. Try to feel that scale, not just intellectually, but viscerally. Every human who ever lived, every thought, every civilization, every war, every work of art, every moment of joy or suffering, compressed into a region of space that may be cosmically negligible. Yet here's the twist that transforms this from existential dread into profound empowerment. We know this. From our tiny vantage point, we have decoded the structure of reality across scales spanning 30 orders of magnitude, from subatomic particles to the observable universe. We have measured the age of the cosmos to within 1% accuracy. We have mapped the afterglow of creation with exquisite detail. We have discovered dark energy, dark matter, cosmic inflation. We have tested general relativity to extraordinary precision. We have calculated expansion rates and predicted the far future of the universe. We may never see beyond the observable horizon directly, but we can infer what lies there through mathematics, observation, and the consistency of physical law. We can constrain the size, shape, and fate of the cosmos. We can predict which galaxies will forever remain unreachable and calculate the ultimate limits of observation. That is not insignificance. That is cosmic awareness. That is intelligence wrestling with infinity and coming away with answers. And the process continues. JWST is rewriting the early history of galaxies. Gravitational wave detectors are opening a new window onto violent cosmic events. Upcoming missions will map dark energy's effects in unprecedented detail. Theoretical physicists are probing quantum gravity, seeking a unified theory that merges relativity with quantum mechanics. Each advance sharpens our picture of the beyond. But let's return to the human experience of all this. When you look up at the night sky, photons that have traveled for millions or billions of years strike your retina. You are literally seeing the past. The Andromeda Galaxy, visible to the naked eye on a dark night, appears as it was 2.5 million years ago, when our ancestors were just beginning to use stone tools. Light from distant quasars set out when the universe was young, and the Earth didn't yet exist. Those photons journeyed across expanding space, through voids and clusters, surviving cosmic time to end their voyage in your eye. And yet, for all the vastness you perceive, you are seeing only the nearest cosmic neighborhood. The overwhelming majority of the universe remains hidden, not because it is dark or obscured, but because its light has not yet arrived, or never will. The cosmic horizon is not a wall. It is not a place where space ends. It is simply the farthest distance light has had the opportunity to travel since the Big Bang. As the universe ages, this horizon grows. New galaxies drift into view. But because expansion accelerates, there is a maximum observable distance we will ever achieve. A future horizon beyond which no light emitted today will ever reach us, even in the infinite future. Current estimates place this ultimate horizon at roughly 60 to 63 billion light-years co-moving distance. Everything beyond that is forever sealed off. So here's the existential question. Does the beyond matter if we can never observe it? Scientifically, absolutely. The simplest models explaining our observations, inflationary cosmology, General relativity, the standard model of particle physics, make claims about the entire universe, not just our bubble. The curvature we measure, the spectrum of density fluctuations in the CMB, the abundances of hydrogen and helium, the distribution of large-scale structure, all are fingerprints of processes operating on scales far larger than what we see. By testing these predictions within our horizon, we learn about physics beyond it. Philosophically, the beyond confronts us with limits, as we live in an era where technology has pushed boundaries relentlessly, exploring the deep ocean, splitting the atom, landing rovers on Mars, imagining black holes. Yet the cosmic horizon is a boundary we cannot cross. Not with faster rockets, not with better telescopes, not with any conceivable technology. It is a limit imposed by the structure of space-time itself. But recognizing that limit is its own form of knowledge. It reframes our place in the cosmos. We are not central. We are not special. We are observers embedded in a vastly larger structure, equipped with intelligence and curiosity, powerful enough to deduce truths beyond direct experience. And perhaps that's the most profound realization of all. The universe does not require our observation to exist. It was here long before us, and it will continue long after. The beyond is indifferent to whether we see it. Yet we, finite beings on a small planet, have glimpsed the rules governing all of it. The equations that hold everywhere, the constants that define reality's behavior, the history written in light and gravity. That's not insignificance. That's connection. That's understanding that we are part of something incomprehensibly large, yet governed by principles we can grasp. So when you look at the stars tonight, remember, you are not looking at the edge of existence. You are looking at the edge of information that has reached you so far. Beyond that glow, reality continues. More galaxies, more stars, more cosmic history, possibly without end. And that continuation, whether we ever witness it or not, is part of the same universe that created you. Now, I want to hear from you. What do you think lies beyond the observable universe? An endless expanse of galaxies stretching forever. A finite but unimaginably large cosmos that loops back on itself. Other bubble universes with different physics. Drop your wildest, boldest theory in the comments below. If this journey through infinity shifted your perspective, share this video with someone who loves staring at the stars and wondering what's out there. And subscribe, because we're going deeper, exploring black holes, quantum mechanics, the fate of the cosmos, and every mystery the universe dares us to unravel. The horizon was never the end. It was only the beginning. Keep looking up and never stop questioning what lies beyond.